So, if you've spent any time online lately, you've definitely run into tools like ChatGPT. I mean, they're everywhere, writing articles, answering impossible questions, even churning out code. It honestly feels a bit like magic, right? But this revolution, it didn't just appear out of nowhere. Let's pull back the curtain and unpack the decades of incredible work that finally taught computers how to talk. And just to give you a sense of how big of a deal this is, look at this number, 100 million. That's how many active users ChatGPT got in just 2 months. That's insane. That kind of growth just doesn't happen. It was the signal to the entire world that something fundamental had just shifted in how we work with computers. But it all comes back to this one really basic question that researchers have been wrestling with for years. A computer gets ones and zeros. It doesn't get language, it doesn't get sarcasm or poetry. So where do you even start? How do you teach a machine the meaning of a single word? That's the core challenge, the whole nut to crack. Okay, so the first big attempt was this really clever idea called bag of words. The name kind of gives it away. The concept is simple. You take a sentence, you break it up into all its individual words or tokens, and then you just count them. You literally create a list of numbers that says this word appeared 3 times, this one appeared once, and boom, you've turned a sentence into numbers a computer can crunch. And this really shows you the genius and, the huge flaw of these early methods. It was a brilliant first step for turning language into math. But here's the problem. The computer has no idea that the word king is related to queen, or that happy is the opposite of sad. To the machine, they're just different items in a list. The meaning is completely lost. The next massive leap forward came in 2013 with a model called Word2vec, and this was a true game changer. This is where we finally started to capture the actual semantic meaning of words. It introduced this idea called embeddings, which you can think of as unique numerical fingerprints for every word. So, how do these fingerprints work? Well, imagine we score words based on a bunch of abstract ideas. For instance, the word baby might get a high score for being human and newborn. Meanwhile, Apple scores really low on those, but maybe high on is food. These scores, this collection of numbers, that's the word's embedding. And suddenly, computers could see that words with similar properties, like king and queen, should have very similar looking numerical fingerprints. But there was still a huge problem. Words don't just exist on their own. Context is everything. Think about the word bank. I can say, I'm going to the bank to deposit money. Or I can say, let's have a picnic on the riverbank. Same word, totally different meanings. These early embeddings couldn't tell the difference. They were static, one size fits all. And the solution to this context problem is this amazing mechanism called attention. The best way to think about it is like a spotlight. As the model reads a sentence, the attention mechanism shines a spotlight on the other words that are most important for understanding the word it's looking at right now. It learns to pay attention to the right clues to figure out, okay, is bank about money or is it about a river? This idea was so ridiculously powerful that in 2017, a paper came out with this now legendary title. It introduced a brand new architecture built entirely on this attention mechanism, throwing out all the old, slower methods. And they called it the transformer. The transformer is, and this is no exaggeration, the foundation for basically every modern large language model you've ever heard of, including GPT. Because it's only based on attention, it can look at a whole sentence at once, not just word by word. This made training way, way faster and let it build a much richer, deeper understanding of context. Right after it was invented, the transformer kind of split into 2 main families. On one side, you have what are called encoders, like Google's BERT. These guys are masters at understanding language. Think of them as the brain behind a super smart search engine. And on the other side, you have decoders, like GPT. Their job is to generate language, to write, to talk, by always predicting what the very next word should be. And with that GPT family, a race began to just make them bigger and bigger and bigger. A model size is measured in parameters. You can sort of think of them as the neural connections in its brain. And the growth, as you can see, was just exponential. GPT-1 had about 117 million parameters. Then GPT-2 jumped to 1.5 billion. And then GPT-3 came out with a mind-blowing 175 billion. This incredible scaling is what unlocked the amazing abilities we're seeing today. Now, as you can imagine, training these monster models costs a fortune. So the community developed a really smart 2-step process. First, you pre-train the model on just a colossal, unbelievable amount of text from the internet. This is where it learns grammar, facts about the world, and even some reasoning skills. Then you fine-tune that already smart model on a much smaller, more specific set of data to teach it a particular task, like how to be a helpful chatbot. So, how can you actually get your hands on this tech? Well, there are two main paths. You can use proprietary models, like the ones from OpenAI or Anthropic, through what's called an API. It's super easy, you don't need a powerful computer. Or you can use open models. These are models you can literally download and run on your own machine. This gives you way more control and privacy, but it does take a bit more technical skill and some serious hardware. As we start using these incredible tools, it's really, really important to remember what they are and what they aren't. They don't think or understand the way a person does. They're extremely sophisticated pattern matchers. And that means sometimes they can generate stuff that sounds perfectly correct but is totally wrong. People call this hallucination. And also, remember, they're just a snapshot in time. Their knowledge cuts off when their training data ends, so definitely don't ask them for today's weather forecast. So we've gone from just counting words in a list to building these gigantic models with billions of connections that can grasp context and generate text that feels, well, human. It has been an absolutely wild journey, and it leaves us with one final, really fascinating question. Now that we've finally actually taught computers how to talk, what are the most important things we should be asking them?